From the beginning of this unit, we've talked about laws of electricity. We've talked about charging objects and the law of conservation of charge. We've talked about electric forces, right? The force of attraction or repulsion between two charges. We've talked about electric fields, those areas of influence that surround objects with charge. Today we're going to talk about energy in the context of electricity. But before we talk about it in the context of electricity, I want to talk about it in the context that you're quite familiar with first, and that's gravity. You guys know, if you think back to Physics 20, that the work done against gravity is equal to the change in gravitational potential energy. Let me give an example of that, and it will make sense to you when I do give you that example. I've got this board marker in my hand right now. Its potential energy relative to the desk is 0, because it's basically on the desk right now, right? In my hand at the surface of the desk. If I raise that board marker up into the air, I change its gravitational potential energy. Let's say I give it 1,000 joules of gravitational potential energy. Well, how much work did I need to do on the board marker to change its potential energy by 1,000 joules? I had to do 1,000 joules of work. So the work done against gravity is equal to the change in gravitational potential energy of the board marker or of whatever it is that's being lifted up. Mathematically, we'd say delta E is equal to W. That's not new. We did that in Physics 20. So why are we talking about this right now in Physics 30? Well, for the same reason we talked about Newton's law of universal gravitation when we introduced Coulomb's law. There's a lot of similarities between gravity and electricity. One of them is the force of attraction, right? That law of universal gravitation versus Coulomb's law. The equation is almost identical. The field lines are almost identical. But when we talk about electricity, electrical energy, it's almost identical as well. We can say that work done in an electric field on a charge is equal to the change in potential energy as well. But this time not gravitational potential energy, but rather electric potential energy. So if I lift a board marker a certain distance up into the air, I change its potential energy by the amount of work that I did. If I move a charge in an electric field, I change its potential energy by the amount of work that I've done to it. Before we go no further, we probably should digress a little bit and define energy, right? If we're talking about the change in electric potential energy, we should probably define electric potential energy. Let's go back once again, though, to gravity before we do that. How did we define in Physics 20 gravitational potential energy? You guys remember? Give me a definition, whether it's exactly the one that myself or Mr. Kader gave you or not. Give me a definition for gravity potential energy. Tell me if this is a good one. The energy stored in an object due to its height. Does that sound like a pretty good definition? Yes? Who says yes? It sounds good to me. Okay, it sounds like a good definition to me. You know what? It is a good definition. It's the definition that you got effectively, and it is a good definition, but it's not quite perfect. Here's the reason it's not quite perfect. Gravitational potential energy is not really the energy that's stored in an object a certain height above the Earth. It's not really the energy stored in this board marker as it's above the Earth. It's the energy stored in the system of the board marker and the Earth. The reason we say it's the energy stored in the object, the board marker, for instance, is because the Earth is so massive that it effectively has no potential to come to the Earth, to come up to the board marker, right? It's the board marker that has all the potential to move. The Earth has effectively none, right? When we're dealing with gravitational potential energy, that's almost always the situation. We've almost always got a big object and a little object. And although technically the energy is the energy stored in the system of the big object and the little object, we usually just say it's the energy stored in the little object due to its height above the Earth. It's really the energy stored in the system due to the distance between the two masses. Well, with gravity, it's okay to approximate it as the energy stored in this little object, because we're almost always dealing with that little object as compared to the big object like the Earth. But with electricity, we're more often dealing with two things that are more similar, not in mass, but in charge. So because of that, we can't just say it's the energy stored in a charge due to its height above something else or due to its distance from some other charge. Rather, this time, we're going to say it's the energy stored in the system of two charges a certain distance apart, which is really much like the gravitational energy definition, just not the definition that we usually use. The approximation that we usually use is the energy stored in the board marker a certain distance above the surface of the Earth. But the real definition is the energy stored in the board marker and the Earth a certain distance apart. You are about to see what may be the easiest problem in all of Physics 30. It is a ridiculously easy problem if you remember that the change in electric potential energy is equal to the work done. If you don't remember that, then it's not such an easy question. Let me show you the question. It says, moving a small charge from one position to another in an electric field requires 3.2 times 10 to the negative 19 joules of work. We want to know what the electric potential energy gained by the charge is. In other words, we want to know what the change in potential energy is. Okay, so we've got work, and we want to know what delta E is. Anybody want to answer that for me? What is it, Bryce? Good. It's 3.2 times 10 to the negative 19 joules because work is equal to the change in energy. That is ridiculously easy if you remember that W is equal to delta E. If you don't, then you're going to be looking at this and saying, I don't know, I don't have enough. I don't have enough information. There's no way I can solve this. Okay? Remember the definition, it becomes a really easy question. I'm going to give you two questions here, and I'm going to give you about 30 seconds to answer them. Basically, just enough time to read the questions. Let's answer the first one, guys. Yep. Right, 1.6 times 10 to the minus 19. This is how much energy is gained. The change in energy, it's equal to the work done. What about the second one? A little bit harder, because you got to do some subtraction. Here's what energy we have. Here's what energy we had. The change in energy is the difference between the two, and work is equal to the change in energy. So the answer would be? Same answer as it was in the last one. 1.6 times 10 to the minus 19. Good. All right? Let's take this a step further. We've got two parallel plates. We'll make these plates vertical. Doesn't really matter, but got them vertical. Those two parallel plates have an electric field that exists between the two of them. In this case, it points to the right. Let's say we've got a positive charge up here. Let's say we've got a negative charge down here. The positive charge will experience a force in the same direction as the field, and the negative charge will experience a force opposite to the direction of the field. If I was to physically take these charges and move them against the field, right? We know that if they move with the field, then the electricity does the work. But if I was to take these charges and move them against the field, cause the motion of this one to be this way, cause the motion of this one to be this way, then I would have to do work to overcome the electric field. The change in energy of these charges, whether it's caused by by the electric field, or whether it's caused by the external force that I apply, is equal to the change in potential energy, whether it's a gain or a loss in potential energy. Right? That's not new. We just went through that. But of course, just like in Physics 20, we also know that that change in energy of that work is equal to F times D. If we're talking about the force, the electric force, and therefore the work done by electricity, then we might be able to replace that F with Q times E. Remember, that comes from the experiencer equation. Or in any case, we might be able to replace that force with F is equal to M times A. Generally, these problems are fairly straightforward as well. Okay? You've just introduced a couple more variables, force and displacement. Remember delta D when we were talking about parallel plates? That was the distance between the plates. Delta D here isn't the distance between the plates. It's the distance or the displacement of the charge as it's moved between the plates. I got another term for you. This one's a bit new. So we've talked about electric potential energy and potential energy difference, which is work. Now we're going to talk about electric potential. Listen carefully to the difference there. Electric potential energy, electric potential. Potential is clearly related to potential energy, but it's not the total amount, but rather it's the amount per unit charge, per coulomb of charge. Let me give you an analogy. Just drop your pens for a second and listen, then you can write it. Say there's 20 of us in the room right now. There's not quite, but it's easier math if we say there's 20. 20 of us in the room right now. We've got $100 combined. Okay, total of $100 in this room right now. If money is analogous to energy, and we are all analogous to charge, then the total energy we have is 100, right? The energy per charge that we have is 5. So the potential energy would be 100, the potential would be 5. Does that make sense? The energy per coulomb of charge, not the total energy, but the amount of energy per charge. Potential is a capital V, not a lowercase v. It's not speed or velocity. It's a capital V, and it's equal to EP over Q. The units would be joules per coulomb. But it just so happens that 1 joule per coulomb is exactly the same thing as 1.0. Anybody want to take a stab at this? No, just volts. 1 joule per coulomb is exactly the same thing as 1 volt. Remember we said the unit for potential difference last week was volts. Potential isn't quite the same thing as potential difference, but it's real close. Let's talk again about potential difference now. Potential energy difference, or work. Potential difference. Well, potential difference is the difference in electric potential energy per coulomb of charge. Or in other words, it's VF minus VI, the final potential minus the initial potential. Well, if potential is E over Q, then potential difference would be delta E over Q. This equation, by the way, right here, appears on our data sheet. This one doesn't. This one doesn't, but that's okay, because in the end, it's a pretty easy one, right? Potential is V, potential difference is VF minus VI. This one's the more important one. One more final thing before we wrap it up. When I'm driving down the highway in my car, I could say that I'm traveling at 100 kilometers per hour. I could also say that I'm traveling at 62 miles per hour, or I could also say that I'm traveling at 28 meters per second. They all mean the same thing, right? Roughly mean the same thing. We can measure speed in kilometers per hour, miles per hour, meters per second, or some other set of units. Generally, we use whatever is the most convenient, which often ends up being meters per second. Energy, we always measure in joules, right? Well, today, for the first time, you're going to learn there's another set of units that we can use for energy as well. There's more than one more set, but one more set that we're going to learn today. The set of units that we're going to learn for energy today is called an electron volt. An electron volt is not potential difference. It's energy. Just like joules are energy. It's just a different amount of energy, that's all. It's defined as the amount of energy that's lost or gained, depends on which way the electron is going, whether it's speeding up or slowing down. The amount of energy that's gained or lost by an electron when it passes through a potential difference of 1 volt. The value of an electron volt is 1.6 times 10 to the minus 19 joules. That's the same as the charge of an electron, and it's not a coincidence. It's not a coulomb there, but it's not a coincidence that it's the same number. The good news is that conversion factor is also on your data sheet. on the left-hand side of your data sheet. So if you ever need to convert joules to electron volts or electron volts to joules, and guess what? You will have to. The conversion factor is there on our data sheet. We'll spend a little bit of time tomorrow showing you how you'd actually go through that process of converting it.